Engineering requires enforcing stability onto physical systems that are naturally prone to drift. Consider the mechanics of this ball and beam apparatus. A DC motor turns a lever arm to balance a free rolling sphere on a tilting track. The entire system is driven by a single physical input, the raw voltage applied directly to the motor's armature. To maintain control, we measure two distinct outputs, the motor gear angle and linear ball position. Mastering the coupled dynamics of this mechanism serves as a rigorous proving ground for classical control architecture. The requirements for this mechanism are strict. The motor must reach a reference speed of 100 radians per second in less than 1.2 seconds. This graph maps our precise performance target. Notice the boundary at the top. The system must settle within a narrow 2% error band, eliminating virtually all variance. Attempting to achieve this precision through physical trial and error risks hardware failure. The parameters must be translated into a digital simulation first. We construct this mathematical translation and tune the controller exclusively within the MATLAB and Simulink environments. Building a model-based simulation acts as a mandatory safety protocol. It allows us to decouple and analyze complex physical interactions before routing power into the hardware. To build that simulation, we have to look past the beam itself and examine the microscopic physics operating inside the DC motor. The motor's electrical behavior is strictly governed by Kirchhoff's voltage law. This schematic illustrates the electrical circuit, mapping applied voltage, inductance, resistance, and the opposing back EMF loop. Moving right, a mechanical free body diagram tracks the shaft, its motion determined by factoring applied torque against inertia and friction. These independent electrical and mechanical systems are permanently coupled together by the motor's internal constants. While these time-domain differential equations describe the physical reality of the motor, they cannot be directly processed for software-based classical control design. We need a mathematical transformation. To digitize these equations, we use the Laplace transform. This operation bridges the gap, converting complex differential calculus into manageable algebraic equations within the S-domain. By combining the electrical and mechanical equations, we generate this unified transfer function, G of S, which represents the entire coupled motor plant. For a systems engineer, this algebraic block represents control. The physical mass and electricity have been successfully isolated into a controllable digital entity. Converting time-domain physics into an S-domain transfer function is the step that makes digital proportional integral derivative, or PID, tuning possible. With the plant modeled, we face a central architectural decision in Simulink. Do we manage the system with one feedback loop or multiple? This flowchart illustrates a standard single-loop logic. It continuously compares the ball's position directly to the target and adjusts the motor voltage in one sweep. But the physical realities of the ball and beam create a mathematical flaw known as a triple integrator. As shown by the expanding distortion, this triple integrator inherently introduces a severe 270-degree phase lag into the feedback signal. If applied to physical hardware, this delayed signal commands the motor to rotate so sharply it can physically damage the lever arm mechanism. A single-loop topology is difficult to stabilize for multi-degree of freedom systems. The architecture requires a redesign. The solution is a cascaded control architecture, splitting the task between two distinct loops. This diagram shows the inner loop, which is tasked exclusively with controlling the motor's gear angle. Wrapping around it is the outer loop, which relies on that stabilized inner motor to dictate the ball's final position along the beam. With the architecture set, we apply specific PID tuning parameters to the Simulink blocks. We set the proportional gain to 1, driving immediate arrow correction based on current variance. An integral gain of 10 eliminates the steady-state arrow, while a precise derivative gain of 0.01 dampens the reaction to prevent overshoot. By isolating the fast dynamics of the motor from the slow dynamics of the rolling ball into cascaded PID loops, we achieve mathematical stability while remaining within the safety limits of the mechanical hardware. The final step is verifying the success of this architecture through the Simulink output data. This top chart plots the motor speed response, showing a smooth climb that flattens against the 100 radian per second reference line at exactly 1.2 seconds. The curve shows negligible overshoot. The velocity stabilizes precisely on target. This bottom chart tracks the torque response, driven by the inner loop's current regulation, rapidly locking onto its reference threshold at 0.5 seconds without dangerous voltage spikes. This damped, controlled torque response ensures the physical lever arm operates within its mechanical tolerances. These tight tracking metrics prove that the cascaded PID architecture has successfully managed the unstable physics of the plant. The ball and beam mechanism is an academic apparatus, but the engineering protocol it requires applies to any complex automated system where precision is mandatory. Model-based software development enables this level of industrial performance. Simulating the plant dynamics in MATLAB allows engineers to expose hidden mathematical flaws, like a 270-degree phase lag, long before deploying logic to a real-time hardware controller. Moving away from hardware-first trial and error reduces the risk of mechanical damage and improves development efficiency. This ball and beam study demonstrates a fundamental shift. Physical behavior is no longer managed through manual tuning, but through the precise digital logic used to model and govern the plant.